Bleeding means removing air from a hydraulic system. When pressure is applied to liquid in a hydraulic system, the liquid does not compress into a smaller volume. Pressure is transmitted without loss. Gases, however, are compressible. Pressure applied to air changes its volume, and some pressure is lost. That is why, if air enters a hydraulic braking system, it can be dangerous. Pressure on the brake pedal will not be transmitted in full through the system to apply the brakes. The brakes will be spongy. Bleeding the brakes means removing this air so that only liquid is left in the system. Friction is a force that resists the movement of one surface over another. It can be desirable, but often is not. It is caused by surface rough spots that lock together. These spots can be microscopically small, which is why even surfaces that seem to be smooth can experience friction. Friction can be reduced, but never eliminated. Friction is always measured for pairs of surfaces using what is called a coefficient of friction. A low coefficient of friction for a pair of surfaces means they can move easily over each other. A high coefficient of friction for a pair of surfaces means they cannot move easily over each other. Hydraulic pressure is transmitted through liquid. Since liquid is effectively incompressible, pressure applied to a liquid is transmitted without loss throughout the liquid. In a braking system, this allows a force applied to the brake pedal to act upon the brakes at the wheels. Hydraulic pressure can transmit increased force. Since pressure is force per unit area, the same pressure applied over different areas can produce different forces, larger and smaller. This system has cylinders of different sizes. When the brake pedal is pressed, the force against the piston in the master cylinder applies pressure to the fluid. This same pressure is transmitted throughout the fluid, but it has a different effect on each piston in the other cylinders. The top cylinder is smaller than the master cylinder, so the force it exerts will be less than the force applied to the master cylinder. The middle cylinder is the same size as the master cylinder, so the force from it will be the same too. The bottom cylinder is larger than the master cylinder, and so is its force. Most of a vehicle's weight is supported by its suspension system. It suspends the body and associated parts so that they are insulated from road shocks and vibrations that would otherwise be transmitted to the passengers and the vehicle itself. However, other parts of a vehicle are not supported by the suspension system, such as the wheels, tires, brakes, and steering and suspension parts not supported by springs. These parts are all called unsprung weight. Generally, unsprung weight should be kept as low as possible.
This section examines basic principles of the hydraulic braking system. Several factors can influence vehicle braking: road surface, road conditions, the weight of the vehicle, the load on the wheel during stopping, different maneuvers, and of course the tyres on the vehicle. An effective braking system takes all these factors into account. A basic hydraulic braking system has two main sections: the brake assemblies at the wheels and the hydraulic system that applies them. There is a brake for when the vehicle is in motion, usually a foot brake, and a park brake for when it's stationary, usually operated by hand. Some systems have all drum brakes. Some have disc brakes on the front wheels and drum brakes on the rear. Others have all disc brakes. A basic braking system has a brake pedal, a master cylinder to provide hydraulic pressure, brake lines and hoses to connect the master cylinder to the brake assemblies, fluid to transmit force from the master cylinder to the wheel cylinders of the brake assemblies, and the brake assemblies, drum or disc that stop the wheels. The driver pushes the brake pedal. It applies force to the piston in the master cylinder. The piston applies pressure to the fluid in the cylinder. The lines transfer the pressure to the wheel cylinders. And the wheel cylinders at the wheel assemblies apply the brakes. Force is transmitted through the fluid. For cylinders the same size, the force transmitted from one is the same value as the force applied to the other. By using cylinders of different sizes, forces can be increased or reduced. In an actual braking system, the master cylinder is smaller than the wheel cylinders, so the force at all of the wheel cylinders is increased. When brakes are applied to a moving vehicle, they absorb the vehicle's kinetic energy. Friction between the braking surfaces converts this energy into heat. In drum brakes, the wheel cylinders force brake linings against the inside of the brake drum. In disc brakes, pads are forced against a brake disc. In both systems, heat spreads into other parts and the atmosphere. So brake linings and drums, pads and discs must withstand high temperatures and high pressures. On modern vehicles, this basic system has some refinements, such as a power booster. This helps the driver apply the brakes. This section examines divided systems for ABS. Modern cars use tandem master cylinders to suit divided or dual-line braking systems. A divided system is safer in the event of partial failure. Fluid loss in one half of the system still leaves the other half able to halt the vehicle, although with an increase in stopping distance. A wheel's braking ability depends on the load it's carrying during braking, so the type of vehicle is a major factor in how its system should be divided. A front-engined rear-wheel drive car has around 40% of its load on its rear wheels, so its braking system can be divided in a vertical or front-rear split. This puts the front wheels in a different system from the rear wheels. If one half of the system fails, the front or the back, there's still enough separate braking capability left in the other half to stop the vehicle. This doesn't work well for a front-wheel drive vehicle. A load of about 20% on the rear wheels can't provide enough braking force to stop the vehicle. Front-engined, front-wheel drive vehicles use a braking system split in a diagonal or X. The left-hand front brake unit is connected to the right-hand rear unit, and the left-hand rear to the right-hand front. If one system fails, a 50% braking capability is left in the other system. Dual proportioning valves maintain optimum braking in each system. A system that partially failed would cause severe braking pull on a vehicle's suspension, so suspension geometry is usually revised to counter this. An alternative arrangement for front-engine rear-wheel drive vehicles is an L-split. The front disc brake units have 4 piston calipers. 2 of the pistons on each front unit connect to the right-hand rear, and the other 2 pistons of each unit connect to the left-hand rear. As with the X-split, if there is failure of either half of the system, it still leaves 50% braking capability. This section examines the anti-lock braking system. Applying brakes too hard or on a slippery surface can cause the wheels to lock. When wheels lock, steering control is lost and, in most cases, it produces longer stopping distances. The anti-lock braking system prevents wheels locking or skidding no matter how hard brakes are applied or how slippery the road surface. Steering stays under control and stopping distances are generally reduced. It consists of a brake pedal, a master cylinder, wheel speed sensors, the electronic control unit or ECU, and the hydraulic control unit, also called a hydraulic modulator. The wheel speed sensor consists of a notched or toothed rotor that rotates with each wheel and a pickup. As the wheel turns, a small voltage pulse is induced into the pickup and sent to the electronic control unit. When the brakes are applied, the wheel's speed of rotation changes. This sends a new signal to the ECU. If the control unit detects that a wheel might lock, it sends a signal to the hydraulic control unit. In a 3-channel system, the hydraulic control unit uses 3 solenoid valves to control brake pressure and prevent them locking. The valves are in series with the brake master cylinder and the brake circuits. One operates for each of the front wheels and one controls both rear wheels. At the start of a journey, the ABS automatically checks itself. Any failure in the system lights up a warning light in the dash panel. During normal braking, as the rotational speed of the wheel falls, no electric current flows from the ECU to the hydraulic unit. The solenoid valve is not energized. The brake master cylinder hydraulic pressure is applied to the brake unit, and the ABS is not involved. However, even though the ABS is passive during normal braking, its control module is constantly monitoring for rapid deceleration of any of the wheels. If a wheel speed sensor signals severe wheel deceleration, which means the wheel is likely to lock up, the ECU sends a current to the hydraulic unit. This energizes the solenoid valve. The action of the valve isolates the brake circuit from the master cylinder. This stops the braking pressure at that wheel from rising and keeps it constant. If the sensors signal the wheel is still decelerating too rapidly, the ECU sends a larger current to the hydraulic unit. The armature moves even further and opens the valve. It opens a passage from the brake circuit. Brake fluid is sent from the brake circuit back to the master cylinder. Pressure in the brake caliper circuit is reduced so that the wheel is braked less heavily. If the wheel sensors indicate that lowering the brake pressure is letting the wheel accelerate again, the ECU stops sending current to the hydraulic unit and de-energizes the solenoid valve. This lets the pressure increase so that the wheel is again decelerated. This cycle repeats itself about 4 to 6 times per second. It is normal in an ABS for the valves in the hydraulic control unit to keep changing position as they change the brake pressure that's being applied. These changes in position may cause rapid pulsations to be felt through the brake pedal. This section looks at the brake pedal. The brake pedal uses leverage to transfer the effort from the driver's foot to the master cylinder. Different lever designs can alter the effort the driver needs to make. It is usually suspended from a bracket between the dash panel and the firewall. In many vehicles, the brake pedal is either connected to a switch or in contact with one. It operates the stoplights when the brake pedal is depressed. This section looks at the master cylinder in ABS. The master cylinder is connected to the brake pedal via a push rod. The ABS master cylinder is similar to the tandem master cylinder used in divided systems. It has a primary piston and a secondary piston. The secondary piston incorporates a center valve. This controls the opening and closing of a supply port drilling in the piston. At rest, the supply port is open and connects the reservoir with the front brake circuits. The primary piston still has an inlet port and a compensating port. When the brake is applied, the primary piston moves, which closes its compensating port. Fluid pressure in the primary circuit rises. It acts with the primary piston spring to move the secondary piston forward, closing the center valve. Pressure builds in the secondary circuit. Pressure keeps building in both circuits and applies the brakes in both circuits. If the secondary circuit fails, the secondary piston is forced to the end of the cylinder. When it reaches the end, pressure builds in the primary circuit. If the primary circuit fails, the primary piston contacts the secondary piston and pushes it to operate the secondary circuit. In normal operation, when the pedal is released, the springs in the master cylinder push the pistons back more quickly than the fluid can flow back from the wheel brake units. This creates a low pressure area in front of each piston. Such low pressures can cause air to be drawn into the system. To prevent this, there are recuperating grooves in the primary piston and the seal. Fluid at atmospheric pressure flows through the inlet port and past these grooves. When the primary piston is returned fully, any extra fluid coming back from the brake units displaces fluid into the reservoir through the compensating port. In the secondary circuit, fluid also at atmospheric pressure is forced back into the inlet port. The inlet port connects with the supply port drilling in the piston. Any difference in pressure lifts the center valve from its seat and lets fluid enter the chamber ahead of the secondary seal and prevents low pressures developing. When the piston has returned to the rest position, the seal is pulled off its seat by the action of the link and spring. This lets fluid still returning from the wheel units displace fluid back to the reservoir. If braking conditions are such that the hydraulic modulator must return brake fluid to the master cylinder, then for the front brake circuits, fluid is returned to the front section. This forces the secondary piston back against the force of the primary piston spring and the rear brake pressure. If enough fluid returns, the center valve opens and allows fluid to return to the reservoir. If fluid is returned from the rear brake circuit, the secondary and primary pistons tend to be forced apart. The amount of fluid that returns to the master cylinder is determined by the degree of anti-lock braking control. With approximately 4 to 6 ABS control cycles per second, the rapid changes in pressure cause pulsations that can be felt by the driver at the brake pedal. This section examines brake lines. Brake lines carry brake fluid from the master cylinder to the brakes. They are basically the same on all brake systems. For most of their length, they are steel and attached to the body with clips or brackets to prevent damage from vibration. A flexible section must be included between the body and suspension to allow for steering and suspension movement. These flexible lines are made of reinforced tubing to protect them from objects that could be thrown by the tires. In some vehicles, the brake lines are inside the vehicle to protect them from corrosion. This section examines the proportioning valve. It divides up the braking effort applied to front and rear wheels under heavy braking, according to how load is distributed across a vehicle. The effectiveness of braking force is determined by tire-to-road friction, and this increases as load increases. Applying the brakes causes the front of this vehicle to dip. This causes greater tire-to-road friction on the front tires and less on the rear. This kind of change of load is called load transfer. So if equal braking force is applied to the front and rear wheels, the smaller rear load can make the rear wheels lock and perhaps skid. The braking force applied to the wheels needs to be adjusted to allow for changes in load. The proportioning valve adjusts braking force to allow for load transfer. It can be pressure sensitive or load sensitive. The pressure sensitive valve can be in the master cylinder or in a separate unit in the rear brake circuit. The load sensitive type can be in the body or the axle, where it can respond to load changes and change the braking effort as needed. Master cylinder applications usually combine the proportioning valve with a pressure differential switch. In normal braking, the poppet piston is held in a relaxed position by a large pressure spring. The poppet valve is held against its retainer by a light return spring, and fluid passes freely through the valve to the rear brakes. In heavy braking, master cylinder pressure can reach a valve's crack point. The pressure applied to the two different areas of the poppet piston creates unequal forces. That moves the poppet piston against the large pressure spring. This action holds the conical section of the valve against the seat, which limits the pressure increase to the rear brakes. As greater pedal force increases pressure in the master cylinder, fluid pressure rises on the smaller end of the piston. This combines with the force of the pressure spring to overcome the lower pressure now on the larger end. This forces the piston back, clear of the poppet valve. The increased pressure now acts on the larger end of the poppet piston and again forces the piston forward to contact the valve. When the pedal is released, the pressure of the rear brake fluid unseats the poppet valve, letting fluid return to the master cylinder. The pressure spring now returns the poppet piston to its relaxed position. Should the front brake system fail, the warning lamp spool moves forward, taking the poppet valve with it. Pressure in the rear brakes rises and the piston moves forward, but it can't seal on the valve. Should the rear brake system fail, the warning lamp spool will move backwards to activate the warning light. The proportioning valve doesn't operate in this situation. On a diagonally divided system, the pressure-sensitive proportioning valve is usually located away from the master cylinder. There is one for each circuit. They each operate in a similar way to the pressure-sensitive proportioning valve located in the master cylinder, but without the pressure differential warning light circuit. This section examines the power booster. A power booster or power brake unit uses a vacuum to multiply the driver's pedal effort and apply that to the master cylinder. This increases the pressures available from the master cylinder. Units on petrol engines use the vacuum produced in the intake manifold. Vehicles with diesel engines cannot use manifold vacuum, so they are fitted with an engine-driven vacuum pump. The most common booster now operates between the brake and master cylinder. It increases the force that acts on the master cylinder. Whenever the pedal is depressed, the power brake unit assists the driver. The level of assistance depends on the pressure applied. When the driver moves the brake pedal pushrod, it transmits movement through the power unit to the master cylinder piston to apply the brakes. It also operates a control valve that admits air at atmospheric pressure to the rear of the unit. How it works depends on the position of the pushrod. A hose connects the intake manifold to a vacuum check valve on the power unit. With the engine running, the vacuum in the intake manifold is used to evacuate the power unit. This valve is held off its seat and a vacuum is produced in both chambers of the unit. The chambers are separated by a flexible rubber diaphragm attached to the diaphragm plate. It is held in the off position by a diaphragm return spring. The master cylinder pushrod and the control valve assembly are centrally located on each side of the plate. As the brakes are applied, the pedal pushrod and plunger move forward in the diaphragm plate. This brings the control valve into contact with the vacuum port seat. It closes the vacuum port, sealing off the passage connecting the chambers. Further movement of the pushrod and plunger moves the air valve away from the control valve to open the atmospheric port. Air at atmospheric pressure comes into the air filter and passages and enters the chamber at the rear of the diaphragm. The difference in pressure now on both sides of the diaphragm moves the diaphragm plate forward, and it takes the master cylinder pushrod with it. Hydraulic pressure builds up in the brake system to operate the brakes. As pressure rises, a counterforce acts through the master cylinder pushrod and the reaction disc. This counterforce acts against the plunger and pedal pushrod. It tends to move the plunger slightly to the rear, and it closes off the atmospheric port. If the vacuum source is interrupted, then, as the pedal is pushed down, the pedal pushrod and plunger assembly come in contact with the reaction disc. This forces the master cylinder pushrod forward to operate the brakes. The pedal force needed then is much greater than with vacuum assistance. During application, the reaction force against the valve plunger works against the driver to close the atmospheric port. With both the atmospheric and the vacuum ports closed, the power unit is in a holding position. It stays this way until increased pedal force reopens the atmospheric port, or a drop in pedal force reopens the vacuum port. With the force on the pedal held constant, the valve returns to the holding position. But if the pedal is fully applied, the plunger moves away from the control valve to open the atmospheric port and give full power application. When the brakes are released, vacuum returns to both sides of the diaphragm, so the spring releases the brakes. When the engine is switched off or stops for any reason, no vacuum is available. The vacuum remaining in the booster, held by the non-return valve, will provide for at least one power-boosted application. After this, the brakes will still operate, but without power assistance, they require more effort from the driver. This section examines brake fluid. The brake fluid transmits hydraulic pressure from the master cylinder to the wheels. It is a special fluid with special properties. Most are a mixture of glycerin and alcohol, called glycol, with additives to give it the characteristics that are needed. It must have the correct viscosity for hot and cold conditions. Its boiling point must be higher than the temperature reached by the system. It must not damage seals, gaskets or hoses or cause corrosion. Glycol-based fluids meet most requirements, although they do damage paint. And they absorb moisture, hence the warnings. This is important because as moisture is absorbed, it lowers the boiling point of the fluid. Brake fluid should not be mixed with mineral-based oils or solvents. If contamination is suspected, the braking system must be drained and flushed with a suitable solvent and rubber components replaced. This section examines the hydraulic control unit or modulator of the anti-lock braking system. The ABS control module or ECU sends commands in the form of electrical signals to the hydraulic control unit. This unit executes them using 3 solenoid valves connected in series with the master cylinder and the brake circuits. 1 valve for each front wheel hydraulic circuit and 1 for both of the rear wheels hydraulic circuit. This is a simplified diagram of 1 solenoid valve operating on just 1 wheel. In normal, non-ABS braking, brake pedal force is transmitted to the master cylinder, then through the solenoid valve to the brake unit at the wheel. The signals from the wheel speed sensor show no tendency for the wheel to lock up, so the ECU is not sending any control current to the solenoid coil. The solenoid valve is not energized, and the hydraulic pressure from the master cylinder is supplied to the brake unit at the wheel. When the control unit detects any lock-up tendency, perhaps from too rapid wheel deceleration, it sends a command current to the solenoid coil. This causes the armature and valve to move upward and isolate the brake circuit from the master cylinder. That keeps the pressure between the solenoid and the brake circuit constant, whether or not the master cylinder hydraulic pressure rises. If the sensors signal continuing excessive wheel deceleration, the control module sends a larger current to the solenoid valve. This lowers the braking pressure by moving the armature up further, opening a passage from the brake circuit to an accumulator, a temporary reservoir for any brake fluid that flows out of the wheel brake cylinders because of the fall in pressure. A return pump sends this brake fluid back to the master cylinder. If the sensors then signal the lower pressure has let the wheel speed up, the ECU stops all command current, which de-energizes the solenoid valve. The pressure rises and the wheel is again slowed down. No matter the phase of operation, pressure in the circuit can never rise above master cylinder pressure. This section examines wheel speed sensors. A wheel sensor consists of a toothed rotor that rotates with the wheels and a pickup. As each tooth of the rotor passes the pickup, a small voltage is induced in the pickup. These pulses are sent as input signals to the electronic control unit, which processes them to operate the hydraulic control unit. This section examines the electronic control unit. The electronic control unit receives signals from different sources. A switch at the brake pedal provides a brake operating signal. Another in the ignition system signals the engine is operating. This sets off the automatic check the ABS conducts every time the engine starts. Another input is from the wheel speed sensors. These signals are used to control the hydraulic control unit and anticipate wheel lock. If a wheel starts to lock, the electronic control unit operates the solenoid valves to reduce hydraulic pressure appropriately.